Okay, so what I want to do is start off with the slide that we were looking at last time. This is what we're trying to do is measure first of all, the hydraulic head gradient and then hydraulic head contours in cross section. So what I'm showing here is this sealed tube, and then a part of that tube that we'll see is called a well screen. Here is connected to the aquifer, and this is the water level inside of that sealed tube. So well screen, this would be the casing, and we have the water level like you see there. So what I wanted you to do is tell me what was the hydraulic head gradient and what direction is the water flowing. So what about this one? Hydraulic head gradient. What do you think? Buddy? So it's flowing down. Who says down? Okay. Who says up? Flowing up. So the highest head is here. The lowest head is here. So the way this is working, this head, we measure from the datum, it's whatever that length is, and it applies right there. And this one applies here, so it's going from high head to low head, it's going up. What's the gradient? Just looking at it, what do you think? 10, 100, 50, 10? So it's delta H over delta L. So
0.5.
So delta H is that, and delta L is this, right? So, yeah, 0.5. What about this? Up or down? Yep. High head down, and the head gradient.
0.25.
Yeah. So it's that divided by this. So maybe there are 4. This is about 1/4 of that. And here, up or down? Wait, this side. Somebody.
Yeah.
Down. Okay. So what the highest head is here, right? And the lowest head is here, so it's going up. What's the gradient?
1.
Yes. So that is about the same length as that. So the change in head is about equal to the change in length. Okay, so a gradient about 1.5 or 0.25-ish, 0.5. If you wanted, if you had it on the paper, which I think you do, you could measure. But what I wanted to do is intentionally not measure, just do it by inspection. Okay, the key thing is that is the hydraulic head, that length, and it applies there. So we get like a single value that is a measure of the hydraulic head from that length, and it applies to the screen on the piezometer. Okay, so now I want to expand this concept out a little bit and do a full cross section. So you should have this on your handout. And I guess, kind of see how it's going. The handouts, we sometimes use them the day that I hand them out, but sometimes later. So just bring all the handouts with you. Okay, so here's the cross section. Here's the water table. And we want to apply this concept to do the head contours and cross section. So here's the screen. This one is just kind of drawn out by hand, but here's the screen. So the head is going to apply right here. And this is the measure of what the head is right here. And here's the scale. In this case, the datum is right here. I can put the datum wherever I want. So the datum is right there. And I need to go and fill this out. When we did the head contours in map view, we had the hydraulic heads at a series of points, right? And then we drew in the contour lines. So this will be the same approach. I think I've got a little graphic going on here. Okay. So looks like the out of whack. Let's just go and do it. So let's start out with at the water table. Okay, so here's the water level. This is the water table. So we have a screen here at the water table, and the water level is equal to the water table height. So the head here is like 32. So that applies at that screen. And we got another one here. So that looks like it's 40. And this here, so that screen, we go across and it looks like it's 32. Okay, and this one is 24. Okay, what about here? What would that be? 8. Okay. What about that? 19, yeah. 24. 14. 14. So this, you have a handout. Go ahead and you write this in on your handout because we'll go and do the contours, and then you'll have this as an example. So this looks like 14 here. And 10. Make sure that you're putting the labels at the screen. That's the key thing. And mixing this label for 14 up with that height is the common problem that people have. So this looks like 9, 8, 8, 6. And this is the stream here, so that's going to be 2. That's right at the stream. Okay, so those are points. If we wanted some more points, this is the water table here, right? You see this little triangle. That little triangle means it's the water table. And what was the definition of a water table? Pressure head is 0. Pressure head is 0. So what's the total heading? Is the elevation. The total head is the elevation. So these numbers are total head. So we can get the total head anywhere along here. We did it here because we had some wells, but if we wanted to have a little more, have a supplement, like right here, that's 20. And that would be 10. So we can get some more points if we want them, from the water table. Okay, so those are the hydraulic heads, and now we can draw in the contours. So we've got 40 going down to around 0. Let's first just do, let's just do every 10, and then we'll probably want to split it. So 30 is going to start here. They'll all start at the water table, and then it's going to come through here. It would be like that. So here's where 20 starts, and we're just going to take it to the water table. We're not going to put it up into the data zone. We don't really have any information there. So here's 20. Here's 24 and 19. So 20 is going to come through here. And here's 18 and 24, so it's going to be like this. And we see here, this is a groundwater divide, right, with the water table. So these head contours are going to be kind of flattening out. So we'll have a head contour look like that. And then 10, there's 10, there's 10. So 10 looks like it's going to be like that. And then, it's going down off of the lot. And then 0 is here. We don't really have anything that's at 0. So there's the first 3. That's not quite, that's okay. We can kind of see what's going on. Here's the high head, flow is going like this. But let's put in the intermediate ones every 5. So 35 is going to start here. That 25 would start right here and would go above 24. There's another 24. So there's 25. 15 is right, starting right there, going above 14 and closer to 14 and 19. As something like that. And then 5 would be, there's 4, there's 2, 4, there's, come over here. 5 is right there on the water table. And then it's not coming over here. It goes between 4 and 6. So 5 is going to look like that. And I'll show you why. Well, I'll show you why that makes sense. Okay, so those are the heads. Yeah.
Sorry, are you counting the elevation points at the screen or at the water table?
So at the water table, the pressure is 0, so the elevation equals the total head. So at the water table, I can get the total head directly. But at the screen, that head is given by that elevation. Okay. Yes. So that elevation is 6, it goes there. Okay, so let's do some flow lines. Let's say we're gonna have infiltration coming in like that. So we would enter the water table here. And then the flow is going to be perpendicular to these lines. So it's going to be, we know it's in that direction. To draw it, we're going to cross the line as and be perpendicular, then kind of extrapolate. So it looks like it's going to be that path and then go to the stream. Here, something similar. This curving down, and it's going to go off the page and then come back up here and then be perpendicular to that. Okay, so this head contour curving around is because the flow is converging and going to the stream. And then we have another one up here near the divide, and it's coming like this and going down. And if it was uniform, it would go down here and come back up and go to the stream. Okay, so that's what the flow system looks like. That's, kind of what we've been drawing. So that I think is hopefully is all internally consistent. Okay, see how that all works in cross section? Good. There'll be a chance to practice that. I think that'll be helpful. So here's some rules that I have. You can check out the PowerPoint for these rules. And good. That wraps up what I want to do with hydraulic head contours and interpreting head contours. So I want to change the topic a bit, and we're going to be building on the work that we've done on flow and head contours. We're going to be looking at a little. We're going to start a bit of a different topic. So what I want to do is be able to analyze flow through aquifers, and it's driven by head gradients, but it also is going to be controlled by the properties. So if we want to analyze flow through porous media, we need to know about the transmission properties of the porous media, but also the storage. So remember the basic water balance, the flow in equals the flow out plus the change in storage. So the transmission properties will govern the flow, and the storage properties will be the change in storage. Okay, so we'll need to know about some properties, some processes during the flow and storage. We're going to use then these concepts to develop some equations that we'll then solve in a couple of different ways, and then we'll show you some applications. So that'll take the next several classes to do. So start off with the storage and transmission properties. Here's stuff you should learn today about the primary and secondary porosity. So that'll be an important storage property. This concept of representative elementary volume, that'll be how we can deal with kind of the complexities of porous media. And then these specific yield and effective porosities are some particular kinds of porosity. All right, so if we want to store water in rock, most of in the subsurface, most of the material is solid, and we can't really store any water. And then we store it though in between the solid materials. So if we just conceptualize it in a simple way, then in the subsurface we've got some solid grains like these things here, nice round grains, and then we've got pore space. And some of the pore space is filled with water, and some might be filled with air. And then this is the total volume here. So we've got these various different things, and we'll take ratios of those to describe some basic properties of this material. So here's what some of the grains look like in some idealized cases. Just round or very nearly round. So that's kind of what I had in mind here. But in a lot of cases, it's not this ideal. There are fractures in crystalline rock that form important pores, and then in some cases, fractures or other discontinuities in some rocks can get dissolved out. So they're enlarged, and sometimes they can be quite large. So there's a person in a fracture that's been dissolved by naturally occurring acids, carbonic acid in limestone. So these are kinds of porosity. So we'll want to look at this term porosity. In general, it's the ratio of the volume of voids to the total volume.
in a porous material. So it's the white space and the blue space added together. That volume as a ratio with the total volume here. So there'll be primary porosity and secondary porosity, and then there'll be some other more specific kind of hydro-related variations of this ratio. These are all going to be related to storage, the volumetric water content, the degree of saturation, specific yield, specific retention, and then this one, effective porosity, will be related to flow. Okay, so a basic concept that we're going to use for porosity and other terms like hydraulic conductivity in porous media is a representative elementary volume. So porous media, in an idealized sense, looks like this. It's got these solid grains and then pore spaces, and we want to represent this in an averaged way. We could, in some cases, we could represent it in an actual way, the actual grains and the actual pore spaces. That's possible to do, but it's complex. And it's complex in ways that we often don't want to deal with. So instead of dealing with all the complex geometries of pore space, we want to do it in an average way. So porosity is a way of doing this. So we define porosity as the ratio of the voids to the total. But here's kind of the issue with that, because we could say that that's the volume, or just look at it in 2D. So porosity would be the volume or the area of the voids to the total area. So if that was the area of interest, then the porosity in that area would be about 0.5, right? It's about half void. So that would be the porosity at that location. But if we moved it, then the porosity there would be much higher. And we moved it there, then it would be much lower. If we moved it there, it's all pore space. And so at that scale, porosity doesn't really have a meaningful, it's not meaningful because it goes from 0 to 1. So it doesn't really pin it down. And so what we need to do then is go to a larger scale. And now we have a volume of pores, the total volume that's there. It looks like it's a little bit less than 0.5. And then there it's a bit higher. And we move this volume around and we get different values of porosity as we move it around. But we don't get anything that's totally pores or totally solids. So the range of porosity is kind of necking down a bit here. And if we go to a larger volume like this, then we move that around and we get a smaller range and less variability. So we're starting to get to a size here where averaging the volume of the voids over the total volume is starting to give us a meaningful value. It's kind of stabilizing at a meaningful value as we move this thing around. So we can represent the material within this volume using this single number, and we can represent actually the entire region here with a single number if we're averaging over this. Well, not quite, but if we make it a little bit larger, what we see is that it's going to neck down and give us a single value. Okay, so this thing here, this pink box, is what we call a representative elementary volume. And using porosity as a meaningful term works so long as our region is bigger than right here. Okay, so the size is increasing in this direction and in plus X direction. As long as we're in here, then porosity gives us a meaningful average. And then we go ahead and use it. If we want to do smaller scale work down in here, porosity isn't really going to be very meaningful because it's changing spatially. Now, what happens is that we have this averaging volume that gives us a meaningful term at this size. But in the case of, well, in the case of porosity, but also other terms that we'll use to define porous media, what happens is that we get to a certain size here and it stabilizes. But then as we make this representative volume bigger and bigger, it starts to diverge again. Because if you think about it like this, say we have a layered bed of sand, and then here's some clay, and we have a representative elementary volume that's this kind of usually stabilizes out at 10 or maybe 100 times the size of the grains, right? So if it would be bigger than this, but maybe like this size, then the porosity is going to stay roughly the same as you move it around. So we have a representative elementary volume like this that works for this sand, and we make it bigger and it still is working okay. But as we make it bigger, we start to get into this other material, and then this volume kind of drifts up or drifts down. So the representative elementary volume has kind of an upper limit and a lower limit for where it works. But within that limit, what we can do is take this complex mixture of solids and pore space and average it out to give us just a single term. So that's going to be really a key concept, because without that, analyzing flows through porous media would be a lot more difficult. So here's some examples of what's called primary porosity. These are pore spaces that are created when the rock is formed. And so here's this is a photomicrograph of carbonate rock. So these are former calcite forming organisms that are now fossils, and the blue is the pore space. Here's some beach sand and the pore space between those grains. The blue here is also the pore space. This is a sandstone. So this started out looking like this, and the white is grains. And one of the things that's kind of cool here is you see these, I don't know if you can see these little kind of light lines here. See that?
Yes.
So those are what's called suture lines. And what happens with sands is that if you have grains like this that are let's say they're ideally circular, and they're deposited like that. So this stuff, then when it's buried, you get high stresses, and those stresses get concentrated at the points of contact. And if you have spheres, they're only going to be contacting at a very, very small point. So at those points, the stresses are very high. And when you have high stresses, these are quartz grains. The quartz dissolves away and is removed out, and the grains get sutured together. So if the grains started out like this, then they get pushed together and they end up, and what we're seeing there in the photograph is they look like this, and they have this suture line between them.
because that material has been lost by a process called pressure solution. So that's what's going on there, and that's why the porosity, the pore space is so small, because it's collapsed. Here's another kind of pore space. This is in basalt. These were gas bubbles when the basalt was molten, and then they retained after it solidifies. So you can put a rock in a CAT scan machine and image what the porosity looks like. Here is 22% porosity in a sand. You can kind of see the rounded grains right there. And then that's what the pore space looked like. If you go through some pressure solution, or maybe have some material filling the spaces, the pore spaces, here's what 7% porosity looked like. You can see there's some pretty decent sized pores. But one thing that's important to recognize here is that these fairly decent sized pores are connected by very thin throats, pore throats. See that little strand there? There's another one there. There's one. There's one. That's the way that it works. If you have, if you've got circular grains coming together, to kind of start things off, right there is the pores will be pretty large, but then the connection gets smaller and smaller. So this ends up becoming really important when we're looking at flow through porous media, because the flow is going to have to go, it's going to go through these big pores, but then it's going to have to go through the necks, and often the necks will end up being the part that is controlling the flow, because the flow has to get through that. You can imagine if you had small particles like colloids, they could get screened out in necks like that, or necks, also called throats or throats. So here's some more complex images. This is some shale, and they go and do the CT image and then look at the pores that are connected and pores that are disconnected. Yeah, so one of the things that you can see here, I should point out because it's easier to see here. So see like that one right there, that pore and that one, those are pores that are not connected to any other pores. So you don't really see that. Well, actually, there's one there, maybe, although that kind of goes up to the side. You will have pores that are not connected to other pores, and you also have pores that are not really connected to a flow path. So they go and they're dead end. So what then people are interested in is, what is the continuous flow path that goes through this material? So you could imagine you go through there, go through that little pore throat, there, and go all the way through. So that's the way that fluids could flow. And here with this image, they went in and did some computations, and the red pores here are connected, but the green pores are disconnected. And then the main path that supports flow is this blue path right here. Here's another image of that connected pores and disconnected pores. So these are this is shale, imaging of shale. So doing this kind of study is pretty expensive. You know, just doing the imaging is expensive, but then doing the processing. But 10, 15 years ago, they discovered they could get large amounts of natural gas out of shale by doing hydraulic fracturing. And so the oil industry became very interested in shale and how the pore structure in shale is connected. Because if you want to get natural gas out of shale, you've got to get it to flow through the connected pore space. The disconnected pore space, this green stuff here, if you have natural gas in there, it's not going to really help any, because if it's not connected, you can't get it out unless you create fractures. So about 10 or 15 years ago, there started to be a big increase in these kinds of studies that look at pore structure
in shales and also sandstones in a lot of detail. Here's some more details about that, showing what pore structures look like and how they're connected, and then looking at the organic material. Okay, so that's what the pore structure looked like in what's called clastic material. So clastic material is grains that are made of silicate materials and non-carbonate materials. So another important rock for aquifers is limestone, and it consists of calcium carbonate, and it was formed largely by organisms. And here's a place where limestone is forming today on a reef. So the Floridan aquifer is a good example of a very productive aquifer that is formed from limestone that was once a reef. And here's a quarry in Florida. And this is a cut where they removed some of the material. And if you zoom in on that, this is what it looks like. So these are the pore spaces in this material. And you can see there's that tube there, and then these layers. These are essentially fossils of materials or of organisms that lived on a reef. And it creates large pore structures and fairly well connected, and so very high permeability and plus. Okay, so here are some of the controls on primary porosity, how the grains are packed together, what their shape is, and how they're distributed. So if we take just uniform grains of all the same size, one way that we could pack these grains together is what's called cubic packing. So the centers of the spheres are stacked one on top of another. And packing like that has a porosity, you can calculate it, of 0.48. But you could take the second row and shift it over. And if you take that one and shift it over by half a diameter, then it's going to sit down here in that little low spot. So it's going to look like that. This is called rhombohedral packing, and it has about half the porosity. So just in an idealized way, the primary porosity of material is going to depend on how these pores are, or how these grains are packed together. And this just coincidentally is kind of the range of, well, not coincidentally, this ends up being the range of porosity of well-sorted sands. So from around 0.26 to around 0.48, if you have sands that are roughly 1 grain size, then you expect that kind of a range of porosity. Okay, nice. Well,
What were the range again? 0.26 to 0.48.
yeah. I don't know what's this now.
I think you can just click that green button at the bottom.
Oh, I see. Great, thank you. Okay, so here's another control, grain shape. So here's one kind of shape, a sphere, but there are some grains that are platy. So this is a plate in cross section. Clay minerals, for example, have this shape. And if you have platy minerals, in particular with clays are charged, and so that the surface of the clay tends to stick to the end. So the surface is charged, has negative charge, and that has positive charge, so they tend to stick together like that. And that makes a very loose structure. So as a result of that, clay minerals have a very high porosity, or they can have a very high porosity. And it's it's a consequence of the shape and then the packing that results from that shape. Here's some examples. Kaolinite is a clay mineral. Here's some quartz sand. So clay is going to have porosity in that range. So grain size distribution, if we have a grain size that has if we have a sand that has a single grain size, then it's what we would call very well sorted. And we have a porosity, well, 0.26 to 0.48, right, depending upon what the packing is. But we could have this same material, and if we have in there some grains that are smaller, they're going to fill in the pores. So if we have two grain sizes, the porosity will be smaller than if we just have one. And we could have smaller ones yet, and so on. Okay, so as the degree of sorting decreases, the porosity will also decrease. So here's an example of clean, well-sorted sand, and here's more poorly sorted, some big grains and some smaller grains in between. We can describe that with grain size distribution. So this is the, we basically, you're going to take some sediment and put it through a set of sieves, and the sieves get smaller and smaller, and you measure what percent of the certain size is finer than, or what percent of the material is finer than a certain size. So here's the percent that's finer, and here's the grain size. So if you have a material that plots on that curve, then it's going to be primarily this grain size, like point, there's 2, 3, 4, like 0.05 to 0.08. So that's well sorted material. This material here has material of a broader range of grain sizes. So the degree of sorting decreases from B to A to C. Okay, so the coefficient of uniformity is used to describe the degree of sorting, and that's going to be the ratio of what's called D60. So the diameter of the grains, where 60% of the grains are finer than that. So D60 is going to be, for this stuff, is going to be that's D60. Okay, whatever that diameter is. It's 60%, and go and find what that is. There's 0.01, 0.02, maybe 0.023. And then D10 is here. So there's D10. And we take the ratio of D60 by D10, then we get the coefficient of uniformity. And that's a measure of the sorting. And then we can use that to estimate the effect that the sorting would have on porosity. As the degree of sorting decreases, then the porosity will also decrease. So porosity is porosity that we find in the field is related to the primary porosity, the porosity that was formed when the rock was formed. But there are also processes that cause the porosity to change with time after the rock has formed. So fractures could be created, and that will increase the porosity. There can be chemical reactions where the minerals are transformed from the original mineral to something new. In some cases, that chemical transformation can involve dissolution, where material is removed. And the more pore space is created by dissolution. And then pore space could be created by deformation of material, where the load of the overlying material compresses the grains and shrinks the pore space. So there's an example of a granite with a fracture through it. So the pore space in granite is about around 1 to 2% pore space here. But fractures that cut through can create much larger pores, and those pores will be important for transmitting water through granites. Here's another example of some fractures. This is an example of dissolution and this pressure solution effect. So this zone right here is a place where material has been dissolved away. Here's a larger fracture in some crystalline rock. This is down in Atlanta. So this is an example of a fracture that is similar to a fracture that, well, it's in the same geologic setting as we are here. So weathering will be an important process that creates secondary porosity around here. Here's granite. This is 1 or 2% porosity, but the pink minerals here are vulnerable to weathering. They'll weather for clays, and that increases the porosity. Dissolution is another process where the pores are enlarged. There's some dissolution in that Floridan limestone. And I don't know, does anybody do any caving? No? Okay, it's pretty cool. Go down in there, explore these pore spaces. And then compaction and pressure solution. There's an example of this suturing that occurs as the grains are dissolved away. So here's some ranges that I think would be good to put in your kind of working knowledge. So well sorted sand, we saw sorting. So here's the range, 0.25 to 0.45. And this was kind of dictated by the sorting effect that we saw. If it's poorly sorted, then the lower limit is going to go down about 0.15, and the upper limit would also go down. So that would be a range of poorly sorted material. So clay, there's the range for clay. This is the highest porosity of the commonly occurring materials. Crystalline rock, like granite, so a couple for 1%, sometimes less than 1%, but maybe up to 2%. So that would be a typical range. And then if it's fractured rock, fractured crystalline rock, the low limit doesn't really need to change much. It might go up to 0.05. Okay, so those are some typical ranges of porosity to expect in some common materials that we'll be dealing with. Okay, so I think that's a good place to stop. And I'll see you next time.